Yeah, it's working now. Okay, so we are starting our 38th lecture. So probably two more lectures are needed. So again, I'll just remind everyone today in the tutorial session, I'm going to take a class to just cover up. So that we do not take the class till the end of the till the last lecture day. So I just want to take today two lectures today this time and on when on at 2 p.m. In the tutorial session, and on Monday I'll take my last class probably, and Wednesday, the next Wednesday class, as well as tutorial, as well as Thursday, all these three will remain open for all of you for doubt session. Probably if needed I can take one more class on Wednesday, but I'll try to finish up everything on Monday itself. So then I'll give you some time for asking questions for your final exam and everything. So and I'll just connect the complete course in just one simple flow charts sort of thing, where I can connect the complete course and you will get a good feeling what exactly we did in this course. Okay, so those things will come later on. Let's start our today's lecture. So we were discussing about active and reactive power. Here we have started discussion about AGC, which is the secondary control, or people also call it as a supplementary control. The idea of AGC, again, I'm just reiterating that it is just to bring the frequency back to the nominal value, and also to ensure that the change in the tie line flows are equal to zero. So tie line flows means that if you there are multiple control areas, and if on every control area support each other in general sense, they all support because every control area is connected, so power flows between control areas and they support each other. So idea here is that the tie line which is connected between two control areas, the power should remain as per the scheduled value, not change based on the disturbance within the control area. Right, and then we will see one slide on economics, how economics is ensured in AGC. So we discussed about this, that this was the primary control loop, which is primary speed control or primary load frequency control. Other than this, this tie line, the integrator and speed changer, the frequency changer, this is all participating in AGC. This section of this diagram is actually looking for the AGC, and this is also known as secondary load frequency control loop, or you can also call it as AGC, or you can also call it as supplementary control. Right, so this we will be looking at, and we have seen actually in the last class. Just wanted to reiterate, AGC in the isolated power system, it takes the frequency from the frequency sensor and integrate it and give it to the primary controller set point, load reference set point. It changes that, and based on that the governor action changes and increases the speed if the frequency is required to be increased. And it is AGC is not a mandatory thing, so you can see here the below the second generator is optional, means if it opts for that AGC operation, then only he goes for that. Otherwise he can control its own generator on its own. So he will not be basically allowing the generator to control by someone else, and instead it will control by himself. So we also saw then in AGC, in interconnected power system, we saw before going into the AGC, we saw that, okay, first of all, let's see, if we are talking about interconnected power system, how does the frequency behave? So we saw, we did a small derivation in the last class, that the frequency actually is the same in both the networks. Obviously it will be remain same in all the control areas, but it will be dependent on the load of low frequency sensitive loads present in area 1 and area 2, and the droop characteristics of all the generators within area 1 and area 2. So it is the combination of all the generators and all the loads. And this we saw, you can easily derive, let's say if we increase the load and we did all these expressions, you can put these expressions here and here, and you can just do the mathematical jugglery, and then finally you can arrive that delta F is equal to minus delta PL 1 by R1 plus 1 by R2 plus D1 plus D2. So this derivation you can do. So this I have shown this derivation for the load increase. You can do the same derivation for load decrease, or the generation increase or the generation decrease. Everything you can do here. So here just remember one important point here, this delta P12. So whenever this any load change or anything happens, for this case we were adding actually the load 1 in area 1. So the change in the tie line flows, so this delta P12 will be minus delta PL beta 2 by beta 1 plus beta 2. So beta is nothing but this part. So this is beta 1 and this part is beta 2. Beta 1 is 1 by R1 plus D1 and beta 2 is 1 by R2 plus D2. So it is just the frequency sensitive generation and load in area 1 and area 2. Right? Any queries? So just remember this delta P12, which is delta PL minus delta PL beta 2 by beta 1 plus beta 2. And you can see here that the load change has happened in area 1, but in numerator it is beta 2. So that comes from the derivation. You can do this derivation just by putting the value of delta F in this equation. You can calculate the value of delta P12. Right? Now once we know that the frequency change is same across the network, and we also know if the frequency changes because of some load change, how does this complete area will behave, that we also got to know. Now the idea here is in AGC is the, as I told you before, that the primary objective of AGC was two objectives. One, to ensure that the frequency is coming to the nominal value, right? And the second objective was to ensure that this delta P12 should be equal to 0. We do not want the tie line flows to be changed. It should remain at the value which was scheduled by the system operator. It should not be changed. Generally it is not disturbed, because what happens, you can actually ask me this question, why do we want this area tie line flow to be equal to 0? The idea here is, let's say this is the control area, and here you are looking this control area, it's a very small thing. I'm just saying here there's one generator and one load, but practically control area is to the size of the equal to the state in India. So let's say we are talking about Uttar Pradesh or Madhya Pradesh or Uttarakhand or Delhi or Himachal Pradesh or Punjab. So all these states have many generators and many loads. These states come under one control area. So generally each state has its own operator, system operator. So that operator controls that area. So if a particular operator is controlling an area, that means it's a control area. Right? Now, because if let's say some change has happened or some load change or generation change has happened within an area, like let's say if within Uttarakhand, if some change is happening, so that change, we do not want that change to propagate or to disturb the neighboring areas also. What happens if the change is propagating to neighboring areas? Obviously it will affect the frequencies, and as the frequency is affected, it will also affect the operation of different appliances connected there in other areas also. So basically in a simple word, someone else is doing a mistake, or some load change or something is happening, and everyone is getting punished for that. And because punished means because the frequency will change, even voltage will get affected, then obviously all the loads, as I told you before, that loads means generally they have a specified range for operation between for a voltage and frequency, and if you deviate beyond a particular value, it reduces the life and affects its performance. So therefore we want the frequency and voltage to be constant, and that's why we do not want the disturbance, whatever disturbance is happening within a control area, that disturbance has to be settled within the control area itself, not to be propagated to the neighboring areas. Obviously, if that control area is not capable to satisfy that mismatch, then obviously he can request the neighboring area to help. That is another thing. But primary objective is to ensure that delta P12 is equal to 0. Okay. I hope you got the concept here. Any queries? So now, how to ensure this delta P12 that it should be equal to 0? So the idea here is to ensure this delta P12 equal to 0, and this has to be 0 based on some on the basis of some frequency. Obviously, as the frequency is changing, then only the loads and generation are changing, and that's why the delta P12 is changing. So basically for this we add some frequency bias in the tie line control. This also we saw. So basically we want that area 1 and area 2, this tie line should be equal to the specified value. So what we say, instead of saying that delta P12 equal to 0, we say here ACE. ACE is basically, you can say that, let's say this area is there, area 1. So area 1 is exporting some value or importing some value. So let's say area 1 was exporting some value, let's say 100 megawatt. And it was, this area 2 was importing this 100 megawatt. So let's assume area 1 was exporting 100 megawatt and area 2 was importing 100 megawatt. So area control error for area 1 will be 0 right now because there is no disturbance, and area control error for area 2 will be equal to 0. Now as soon as, and 100 megawatt was scheduled, now because of some frequency change, let's say this 100 megawatt which was exporting, this got reduced to 99 megawatt. So here this area control error will be, for area 1 will be +1 because it is exporting less, so it has to increase its generation to export one more, and area control error for second area will be -1 because it is receiving less the power. So this is basically the area control error. Area control error is whatever, in whichever, let's say this area is there, this is connected to one area here, this is connected to one area here, this is connected to one area here, this. So the net import and export, let's say it is exporting somewhere, it is importing from somewhere, so this net value, this net sum should be equal to 0. That is what is known as area control error, right? So to measure this, or to ensure this part, and to, again I told you before that to smoothly bring the system to the balance, that is the load generation balance has to be there. We want this area control error should be equal to 0. As soon as the area control error goes to 0, that means frequency is naturally coming back to the nominal value. So here obviously, obviously if some change happens, not necessary that all tie line will get affected, there will be some tie lines will get affected, or possibly all tie lines can also get affected. So area control error is measured in this way: delta P12 B1 into delta F. So B1 is the bias, or B1 you can say it's some bias is added based on the frequency to bring the delta P12 back to the nominal value. Right. So basically, change in the delta, this line flow will be equal to delta P12 plus B1 delta F. And that is the change. Delta P1 was scheduled, or it was 0, and B1 delta F will get affected because of some frequency change and some load change or whatever disturbance is happening. So this sum should be equal to 0. If this sum is equal to 0, that means this control area is ensuring that there is no disturbance within its own area. And if there is some disturbance in this value, or if this is not equal to 0, that means there is some mismatch or some issue is there within that area. So basically, every area is responsible for its own area control error. Right? Do you agree with me? So generally this B1 and B2 value is set at beta 1 and beta 2. Beta 1 is the sensitivity, load sensitivity and generator sensitivity with respect to frequency. Beta 2 is the generator and load sensitivity with respect to frequency. So they each bias B1 and B2 is generally equal to beta 1 and beta 2 for its own areas. Right? So now generally we fix this beta 1 and beta 2 to this value, but there is again a big research going on in the. So here basically this load reference set point here, what you saw, this load reference set point will actually change the will continuously keep on changing the load reference set point till the delta P is same as, or the area control error is same as the or area control error is equal to 0. So till we do that, it will keep on changing the governor characteristic, it will keep on changing the turbine speed, so that eventually the frequency or the area control error comes down to 0. So basically, area control error represents the change in area generation. It is mentioned in megawatt. The unit of this bias factor is megawatt by 0.1 hertz, because you want to see how much megawatt change is happening with the change in the frequency of 0.1 hertz. And again, it is applied to the selected units, not all units, because it is the choice of the generator whether he wants to participate in this frequency tie line control or not. So generally the government based power plants generally participate in this. Not all the generators participate in this process, because it affects their operation. Right? Now how to choose this frequency bias? So as I told you before, that B1 is generally kept at beta 1 and B2 is generally kept at beta 2. The idea here is because this area control error 1, if you just put these values of beta 1 and beta 2, so we saw that in previous derivation that delta P12 was delta PL beta 2 by beta 1 plus beta 2. So we saw this derivation before. If you just put this value here, so you'll see that, and if let's say B1 is beta 1, then this will be beta 2 plus beta 1, which will cancel out this part, and eventually whatever is the change in the load within that area 1, the same load change will be taken care in the area 1. So area 1 will generate the same value to satisfy the load change. So basically it is just ensuring that area control is taking care between its own area, within its own area, not requesting the neighboring area. And if you just keep the beta B2 as beta 2, so again if you just keep delta P21 plus B2 delta F, here you can just convert, because P21 is equal to minus delta P12 and plus beta 2 delta F, and you again keep the same value, you will see that the area control error 2 will remain 0 in this case. Right. So whenever that's why people generally keep this value as beta 1 and beta 2. But again, this is again a point of research what value to keep, because if you keep a higher value, let's say do 2 beta 1 and 2 beta 2, if we keep, you'll see that to satisfy the load change, even and here again I just wanted to recap that the load change has only happened in the area 1 and not at the area 2, because I'm everywhere I'm mentioning delta PL1. So that's what so you'll see that for that change even the area 2 is participating here, apart from area 1. And if you keep a small value of a small value of b1 and b2, then area 2 will also participate further, and try to generate or to support this change, and that we do not want. And if you keep a high value, it can affect the control stability, because then again you can see here that all are participating for this purpose. This is going to be a difficult task. So I'm not going into detail here, but I hope you are able to understand what I'm trying to say here. Is there any issues or a query? Please let me know. Okay, if no queries, then let us see a small example here. What exactly I was talking about area control error. Again, I'll just quickly reiterate. Let's say this is area 1, area 2, area 3. Just see the black line is scheduled interchange, that was already scheduled by the system operator. Dashed one is the actual flow. So let's say area 1 was expected to export 150 megawatt, right? And it was scheduled that it will, on this line between area 1 and area 2, 100 megawatt will flow. And it was scheduled that between area 1 and area, sorry, this should be area 3, between area 1 and area 3, it should 50 megawatt should flow, right? So this was expected. But in practice, actually, let's assume some disturbance. Obviously, we cannot ensure that there will be no disturbance, because loads continuously keep on changing. So we cannot ensure that, right? Even there will be some load change in area 1, there will be some load change in area 2 and area 3. So it will continuously be happening. And in practical, when the actual time of delivery came, that time we saw that the tie line between area 1 and area 2, there was a power flow of 120 megawatt, and tie line between area 1 and area 3 was 30 megawatt. So you will see that the net change in area control in area 1 will still be 150. So eventually it is still exporting the same value 150 megawatt. So again you can say that area control error 1 is 0. If whatever is the value, the idea again is that area control error always remains equal to 0 if the net change, or what was scheduled, net export was scheduled was 150 megawatt. Some disturbance has taken place, but even after that disturbances, the net export still remains the same value, then you can say that area control error is equal to 0. So it is the net change. Again, so same is for the area control error 2, that is also 0, area control error 3, that is also 0 at this snapshot. If there is some disturbance apart from the specified value, then obviously there will be some area control error will be there. Right, so this might have given you a better picture how exactly area control error is working. Any queries? So now we are going to see a numerical which will actually help you to understand the complete theory what we have studied. This idea will completely come to your mind in one go. So let us see that if you have no queries so far. So just one slide was remaining before the numerical. That was performance of AGC under normal conditions. So under normal conditions, delta F will be equal to 0. Basically, it will operate at 50 hertz. and this delta P12 will also be equal to 0, or you can say ACE. Even delta P12 can be any value, but eventually the area control error will be equal to 0. So it will ensure that the area control error remains 0 and the frequency remains at 50 Hz. In abnormal conditions, obviously there will be some delta F, it will not be equal to 0, and even the ACE can be equal to 0, but definitely delta P12 will not be equal to 0. So this will also not be equal to 0. Right? So this ACE can or cannot be equal to 0 in abnormal conditions. So I hope you can understand this right now. Okay, so let us start the numerical. Please help me in calculating this, and let us read this problem together and try to understand this problem. Okay, so let's assume there are two areas, area 1 and area 2, right? In both the areas, there is a load of 20,000 megawatt in area 1, and in area 1, generator is having a generation of 19,000 megawatt. And in area 1, we are importing 1000 megawatt from area 2. And in area 2, load is 40,000 megawatt, generation is 41,000 megawatt. Obviously, that 1000 megawatt which extra it is generating, it is being imported or exported to area 1. And across the network, the total load sensitivity is load sensitivity to frequency is 1, and R, or the droop characteristic of all the generators in area 1 and area 2, is 5%. Okay, is question clear to you?
Yes, sir.
Okay, now we are also assuming that in area 1 there is a spinning reserve of 1000 megawatt, which is uniformly distributed across 4000 megawatt of capacity. So basically, it is the idea here is that 1000 megawatt of reserve is there, and among this 19,000 megawatt generations, only 4000 megawatt of generator is participating for reserve, and that too it is uniformly distributed among 4000 megawatt generation, and the spinning reserve is 1000 megawatt. Right. In area 2, there is 1000 megawatt of reserve also is there in area 2, and this is also uniformly generated over 10,000 megawatt of generation. So there is a 41,000 of megawatt of generation in area 2, and among 41,000 only 10,000 capacity of generation is participating for spinning reserve, and that to a value of 1000 megawatt. Right. So I hope now the complete picture is there. Area 1 having a some load, some generation. It is importing some power. Area 2, there is some load, some generation. It is exporting the power. We know the load sensitivity. We know the this droop characteristic, and we know that area 1 is having a spinning reserve of 1000 megawatt. Even area 2 is also having the spinning reserve of 1000 megawatt. I hope the complete picture is there in your mind.
Yes.
Now, let us see some situations. In all these
So,
situations, yes, please.
can you briefly explain the point of spinning reserve?
Sorry.
What is what exactly is the value of 10,000?
So, okay, so here let me just explain both area 1 and area 2. So, area 1 total generation is 19,000 megawatt, but not all the generators are participating. Obviously, there will not be a single generator of this capacity. It's a very huge value, so there will be multiple generators. And obviously, let's assume there are 19 generators of 1000 megawatt capacity. Let's assume that. In that, only 4000 megawatt capacity of generation. So basically, 4000 megawatt means only 4 generator, because I have assumed that every generator is having a capacity of 1000 megawatt. So let's say only 4 generators of 1000 megawatt capacity are participating for spinning reserve, and that too they can only provide spinning reserve of 1000 megawatt, and this is spread uniformly. So they uniformly means they equally share. So let's say it's a four generators, so each generator can provide 250 megawatt of spinning reserve. Does it make sense?
So total spinning reserve is 1,000
Yes,
or separated
in
is
area 1, in area 1 it is 1000.
total.
Yes, yes.
So then what is this 4,000 capacity? Means it is the capacity of that generator.
Okay, let me just make it simple. So let's say this is area 1. Okay, there is one generator, two generator, three generator, four generator. Let's say there are total, this is 19th generator, and each generator is having a capacity of 1000 megawatt. Let's assume, I'm just giving an example. There's no, this is not given in the question and this is not required. I'm just making this up to explain you guys. Okay, so let's assume there are 19 generators in area 1 and all are having a capacity of 1000 megawatt, right? So some will be 19,000 megawatt. This you agree? Now
Yes.
in this it is saying that 1000 megawatt of spinning reserve. If you just quickly read the first sentence for me, that 1000 megawatt of spinning reserve is op- is spread uniformly over a generation of 4000 megawatt capacity. So in this, let's assume, let's take the first four generators here, because all these are generating at 1000 megawatt capacity, and among this 1000 megawatt capacity, only these four generators are providing reserve, because this is now 4000, because I have assumed 1000 megawatt, so that's why these four generators are there. These four generators having a capacity of 1000 megawatt each, so total it is 4000 megawatt, and only these four generators are providing the spinning reserve, and that too of 1000 megawatt only. So that means, and that too it is spread uniformly. So basically this first generator will be providing a spinning reserve of 250 megawatt, second will also provide reserve of 250 megawatt, third and fourth each will provide 250 megawatt. Does it make sense?
Yes, sir.
Now let me just ask the same question for area 2 also. This will make things simple for you guys. Let me just erase this part. Now I'm changing the question here. In area 2 there is total 41,000 generation. Let's say there are only four generators. Let's say four. First generator is generating 10,000, second also 10,000, third also 10,000, fourth is generating 11,000, obviously because the total generation is 41,000. Now the question here is that area 2 has a spinning reserve of 1000 megawatt spread uniformly over a generation of 10,000 megawatt. So which generator will provide reserve here in this case?
Number four.
Sorry, which one?
The fourth one. 11.
Um, Actually, practically, or as per this question, and all four can provide, because all are having a capacity of more than 10,000. Let's say there is one generator, or let's say I'll make this 10,000, and I'll make one generator of 1000 megawatt. Right. So now because it is uniformly spread over 10,000 megawatt capacity, so that means only these four generators can provide reserve. If all four are providing, then each will provide again 250 megawatt, 250, 250, 250. Or what you can say that only first generator is providing the reserve, this first 10,000 megawatt, because this is also a 10,000 megawatt capacity. So here it will provide a reserve of 1000 megawatt. If let's say you assume that there are two generators which are providing reserve, then there will be, both will be sharing 500 and 500 megawatt, because it is spread uniformly. This is also an important word here. I hope you got the
Sir,
idea.
I have a question.
Yes, please.
Yeah, 250 or 2,500.
Sorry, come again.
I think each one of the generators are providing 10,000. So for uh, for the single generator, it will be 2,500, not 2,050.
Actually, it is just an assumption. This generator information is not there. I'm just saying whatever the generation in 41,000 megawatt, among that only 10,000 capacity of generators or the generators which are generating till 10,000 megawatt, they are sharing the total load, total spinning reserve of 1,000 megawatt. So that is the
I
simple
think,
question. Yeah.
yeah, it's going to be 250.
Means you can make any ratio, any assumption you can make, any ratio, any proportion you can make, everything is correct. Only thing is that you have to clearly assume that only 10,000 megawatt portion of the generation is generating 1,000 megawatt of a spinning reserve. So that's what you have to assume. Fine. It will be clear by the questions. We will be seeing all the cases gradually, one by one. So I might take 5 minutes more, but because just let me try to complete the first part of the question, and then later on probably I can complete in the tutorial session. Okay, let me go to the first part. So the first question with in this question in first part of this question is basically, let's assume that in area 1 1,000 megawatt of load is lost. Lost means it is basically shedding or load shedding, or some due to some fault the load is gone. Now there is, in this question, assume that there is no supplementary control. What do we mean by no supplementary control?
No AGC.
Exactly, no AGC, but primary control is still there. So how to solve this question? So we saw that delta F, because we have to calculate the change in the frequency, it will be minus delta PL1, because the load in the area 1 has lost, 1 by R1 plus D1. The droop characteristics of all the generators in area 1, the load sensitivity of all the loads in the area 1, plus 1 by R2 plus D2. So this will be the generator sense or droop characteristics of all the generators in area 2, plus the load sensitivity to frequency in area 2. Right? Do you agree with me on this? There is no supplementary control, so that means there is no AGC. So if as soon as you say there is no AGC, that means frequency is not coming back to the 50 hertz. It will settle down somewhere as the load has lost. It will, you can easily see, because the load was lost, and that means the frequency will increase. Now how will you, what will be the value of 1 by R1 plus D1, or all these values? Let us calculate this. How will you calculate the value of 1 by R1? 1 by R1, or R1 is actually delta P by delta F, or sorry, delta F by delta P. So 1 by R1 will be delta minus delta P, or you can just keep it plus by delta F, because I'm just calculating in per unit value. Right. So 1 by R1 will be delta P by delta F. So what will be this? What will be delta P value here? In the last question, if you remember, in the last class we discussed that if you are or last previous to previous example, we saw that if there is a some reserve is there, we also include the effect of reserve, because it is a spinning reserve and we have to include the effect of that. So total delta P will be 20,000 in the area 1, because 19,000 was the generation and 1,000 was the spinning reserve. Do you remember that? because the generator is ensuring that it will generate that 20,000 megawatt. And what will be the delta F? Because we saw that R is 5% here. So basically delta F will be 5 by 100 into 50. Do you agree with me? Can you calculate this value and tell me? You have to calculate all the value. If you can quickly do that, that will be easy.
Uh, 8,000.
Sorry?
8,000. The
Okay.
value of
8,000. What will be the dimension here? You can see on top it is delta P, in denominator it is delta F, so it will be megawatt per hertz. Now 1 by R2, what will be delta P by delta F? What will be value for 1 by R2 here? So total generation is 41,000 and it has 1,000 megawatt of spinning reserve. So total it will be 42,000 divided by 5 into 50 by 100. What will be this value?
16,800.
How much?
16,800.
Okay, yeah, it will be megawatt per hertz. Now what will be the value of D1? We calculated this previously also. So here D is 1%. Okay, I forgot. So D is 1%. So it will be basically 1% of the total load in area 1. So area 1, it is initially the load was 20,000, but 1,000 megawatt was lost. So actual load is, which will get affected by frequency, is 19,000, and it is divided by the change in the frequency. So frequency is the sensitivity to frequency is 1%. Sorry, numerator it will not be there. So total load is 19,000 divided by 1% of 50. No, this 1% will be there here. And this value will be how much? This should come to be equal to 380 megawatt per hertz. Yeah, so it's 1% by 1%. Yeah, it's okay. So it on top also it will come 1%. So basically 1% of change in load will lead to 1% change in frequency. So both it should come 1 by 100 and 1 by 100. So if you remember, I just do not want to skip that. If you just go to the previous slide, you have seen that it was 1% and 1%. Yeah. And if you do the same thing, it will be 1 by 100 into the load in area 2 is 40,000 by 1 by 100 into 50. So what is the value here? So this should be 40,000 by 50 will be 5 into 8. It will be 800 megawatt per hertz. Okay, do you agree with me? So just put the values here. So it will be minus of minus 1000. So this and this will be 8000 plus 16,800 plus 380 plus 800. What is the value here? What is the value here?
0.0385.
Okay, 0.0385 hertz. So basically, or because the load is lost, so the frequency will increase. The frequency will be 50.0385 hertz. Okay. So now tell me what will be the change in the load. Let us calculate in each area what will be the change. What will be the value of delta PD1. This you can calculate by D1 into delta F. Right? Do you remember this formula? PD2 will be D2 into delta F. Delta PG1 will be delta F by, it is minus R1. Delta PG2 will be minus delta F by R2. Can you tell me the values here? So D1 is 380 into 0.0385 hertz. Delta PD2 is D2 delta F. D2 is 800 into delta F. Quickly, can you tell me the values?
14.63.
14.63 megawatt. What is delta PD2? It is
30.8.
sorry
30.8.
30.8 megawatt. Delta PG1, so it will be minus, because we saw from the diagram that frequency increases, then load increases and generation reduces to basically converge to a value, or to not allow the frequency to increase to a higher value. So minus delta F is 0.0385 into 1 by R1 is 8000. What is this value?
Minus 308 megawatt.
308 megawatt. Okay. And delta PG2 will be minus delta F is 0.0385 into 1 by R2 is 16,800. What is this value?
Minus 646.8.
Minus 646.8 megawatt. Right. Now this is the change. So you can easily calculate in area 1 what is the actual load. Actual load is basically, initially it was 20,000, right? And 20,000, and then 1000 megawatt of load was lost in area 1. So basically load in the area 1 is 19,000, and because the frequency has increased, the actual load in the area 1 will be 19,000 plus 14.63, that is 19,014.633 megawatt. PD2, because there is no change in the load, only 14,000 megawatt was there, 40, and this, because of frequency increased, further load has increased, so eventually the increase will be 0.8 megawatt. Right? PG1, I'll just take 5 minutes and I'll close. PG1, because initially generation was 19,000 megawatt, and because of the increase in frequency, the generation has reduced by 308 megawatt. So it will be somewhere around 18,692 megawatt. Did I calculate it correct? So 8 is 700 and then 300. Okay, initially it was 19,000, right? And then PG2 will be uh, it was 41,000 was the generation. Because of increase in frequency, the generation has reduced by 646, so it will be 40,000 500 uh, sorry, 400, it should be, or rather 300, sorry, 3, or can you help me out? It is 7 will be,
53
sorry,
40,353.2.
yeah, good, perfect. So this will be 4353.2. Now, can you tell me what will be the value of delta P12? What initially it was 1000 megawatt, what is now flowing in that line? So you can just see the area 1 how much it is importing. You do not have to calculate, either you can see area 2 generation minus load, or you can see area 1 generation minus load. So it will tell you how much importing it is happening. So area 1, let's say if I take, so it will be a load is 19,014 minus the generation is 18,692. It will be how much? Somewhere around 700 or 800. It's like 710. Tell me the value. Quickly, what is the delta P12 value? Anyone? Or I have to calculate then. Wait, I'll just. So generation at so you can just do 18,692 minus 19014.63. It
Minus 322.6.
yeah, so basically that will be the generation, or that will be or rather you can say 322.63. So this, so just by the change in the small value of frequency, you can see that the initially it was 1000 megawatt was coming, and now only this much uh, because initially 1000 megawatt more load was also there, that also got reduced. So as soon as you can see that although 1000 megawatt of load was reduced, that means the area 1, if you'll see, both the generation and load is now equal, right? So now if the generation and load is equal, you do not need this 1000 megawatt. But because in area 2 the generation is still at 41,000 megawatt, it has not reduced, so therefore you will still see a power flowing from area 2 to area 1 of 322 megawatt, right? So do you see that? So basically you can also see from here that just to cross check if whatever we did is correct or not. So you can just see the in the complete area. So this area 1 and area 2 combined is a complete system. So you can see that the total sum of PG will be equal to sum of PD. This has to be there, then only the balance will be there. So you will always see whatever we do, either even the frequency is different, the sum of generation will always be equal to sum of load. That has to be there. If that is not there, then there will be an issue. And because here when I say no supplementary control, again what does this mean here is that the frequency or the primary sorry, Mechanical power is actually constant. We are not changing the mechanical power. So that's why the frequency has disturbed, but generation and demand balance will always be there. Right. So there will be few more parts of this question that we will